differential equations. We're looking at day 2 of section 2.5. Looking up here, we've dealt with separable differential equations. We even dealt with that back in BC calculus. Then what did we do? Well, we dealt with the linear, where we had our integrating factors. We had exact or almost exact once we multiplied by an appropriate integrating factor. Yesterday we dealt with the homogeneous differential equations. Today we deal with Bernoulli differential equations. A Bernoulli differential equation is going to be such that you'll have dy dx plus p of x times y q of x. We're used to just seeing that stop there, but if you have y to a power, y to the n, that means we've got a Bernoulli differential equation. It looks so much like the linears. And of course, that's what we're saying right here. If n was equal to 0, that would completely disappear. This would be a linear. If n is equal to 1, we can actually bring the right side over, combine it with the left, and it will be a homogeneous linear differential equation. But what you're going to see is, in general, when n is greater than 1, we're going to make a substitution. Here are our guidelines. U will equal y to the 1 minus n. We'll then find a dy dx in terms of u and a du dx. We will substitute into the original equation. The resulting equation will be linear. We'll find an appropriate integrating factor. We'll solve for u. Once we solve for u, we'll resubstitute back in, and then we'll have our answer. So to get us started, let's first divide by x right here, because you don't like seeing something in front of a dy dx. We can even do that mentally. We'll have dy dx plus, now multiplying by 1 over x is the same thing as dividing by x. And the right side, well, we're just going to drop down a power of x. We'll have y to the second. Now, remember, this right here is kind of like our q of x, y to the n. In this case, n would be 2. And you can see this is now in a Bernoulli form. So we're going to let u equal y to the 1 minus n. In this case, we have y to the 1 minus 2. So u is going to be y to the negative 1, or 1 over y. And I'm going to actually solve for y. I'm going to multiply both sides by y, simultaneously divide by u. Another way to think about it, if u is the reciprocal of y, y is the reciprocal of u. Then I'm going to take a dy dx, and the derivative of 1 over u is negative 1 over u squared du dx. We're assuming that our u is a function of x in this problem. So now what? Well, we're going to come back in and we're going to more or less say, look, wherever we have a dy dx, we're going to make that substitution right here. And likewise, wherever we just have a y, or even a y to the second power, we're going to make use of this other substitution as well. So dy dx, we just said, is going to become, and substituting in, a negative 1 over u squared du dx. That's really just working with that first substitution. I'll say plus 1 over x, but my y is now 1 over u. And if y is 1 over u, when I square that, I'll actually get a 1 over u squared. Now at this point, I hope that you can see that we could multiply by u squared. And if we did that, we'd have a negative du dx. Multiplying by u squared here, one of the u's would cancel. You'd just be left with that. And we'd just be left with an x over here. Multiply through by a negative 1, you'll have du dx really minus your 1 over xu equals negative x. So at this point, I hope you can notice the similarities to what we did at the start of this unit. We started off with linear differential equations where we found an integrating factor. So, this is kind of like our p of x right here. This is like our q of x. And what we did, of course, is we'd always have the integrating factor of e to the integral of our p here. So I'm going to have a negative 1 over x dx. Now, I think we can see already that if we integrate, we'd have an absolute value of a natural log of an absolute value of x. But we're going to solve this for x being on this positive interval. And if that's the case, then this will become e to the negative ln of x, which is really e to the ln of x to the negative 1, which if you think about it, that's just going to be 1 over x. That's your integrating factor. And what we did with our integrating factor, I hope you remember, is we'd come back and we'd multiply every single part of our differential equation by it. So we have du dx multiplied to 1 over x. Multiply by a 1 over x here, you'd get a 1 over x squared. You'd have one more of those. And then on this right-hand side, multiplying by 1 over x, you just have a 1, of course, right? Or a negative 1, pardon me. Well, the whole purpose is now you look at this and say, is this left side really in the product rule? And it is. Look to your du dx to find that. You could say, well, look, I'm taking the derivative of u times 1 over x. We see the du dx. We know we're taking the derivative of that u. Work out the product rule, and you'll see that square bracket right there. Now what? We're going to integrate with respect to x. And nicely, we'll just have u times 1 over x. On this right side, we'll have negative x plus a constant. Then what? How about we multiply by x? We can do that real quickly. We'll have u is equal to negative x squared plus c times x. Well, if we had a function of u, we'd be done. But the bottom line is, if you look back to the very start of the problem, u was equal to 1 over y. That was our original substitution. And of course, we took derivatives, we solved for y first. But the fact is, u is 1 over y. And we have this, negative x squared plus a cx. Right now, it's actually just one further step. Take a reciprocal on this left side. That means you take a reciprocal on the right side. And you could put your cx first minus x squared. And we are done. That is a Bernoulli differential equation.